Hello and welcome to lesson 7. Today we are going to start with some rational functions. You've actually already seen one when we were talking about domain, but rational functions are basically functions where it is a function divided by a different function. This means that rational functions almost always have a limited domain because, divided by 0 and all that. So let's switch over to the board and we'll look at a couple of them. So if we start off with, say, f of x equals, x minus 3 over x squared minus 9. So obviously bottom, right away, bing, bang, boom, limited domain because we can set x squared minus 9 equal to 0. So if we go ahead and do this, we're going to get x squared equals positive 9 because plus 9 plus 9. And then we square root both sides. So when we square root both sides, we get x equals positive or negative 3. So we get negative 3, positive 3. So x cannot be those numbers because we cannot divide by 0. So what that would look like graphically is that would mean, so according to this, negative 3 is off limits. We're not allowed to touch that line. And positive 3 is also off limits, so we wouldn't be able to touch this line. So when we go to look at the actual function, however it works, we know that it will not touch these lines of x equals negative 3 and x equals positive 3 because it's just not possible for us to use those. This means that our domain would be negative infinity all the way to negative 3, but we wouldn't be able to use it, so we'll use parenthesis, union negative 3 to positive 3, and then union 3 to infinity. So basically, we can't use these two numbers. We can use everything except for those two numbers. So this is how we find the domain of a rational function. At least algebraically, this is how we do it. So with that, we'll go ahead and clear the board, and then we will cut back over to the lecture. Okay, so that's what a rational function is. That's how we can check the domain of one. The range of a rational function, however, is a very different kind of animal. And the reason for this is because how fast the top and bottom are in relation to each other is going to determine what y values we are not allowed to have. Because just like x values we're not allowed to have, rational functions also come with y values we're not allowed to have. So let's go back over. Okay, so there are two examples of what we're going to be looking at. Because when we're talking about the range of a rational function, we're looking for what are called horizontal asymptotes. So horizontal asymptotes exist whenever the powers on top and bottom of a rational function are certain things. So let's say, for instance, we have x over x cubed minus 8. So if we go to graph that function, we say x cubed minus 8 equals 0. That means that x cubed is equal to 8, and then the cube root of 8 is 2. So we know, according to this, that x equals 2 is off limits. So that one's not going to work. And what this function is going to look like if we were to actually graph it is that it would start off as being negative. So it starts off as kind of a smaller negative number, and then it gets bigger, 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 bigger. And then if we go to do this again, it'll be bigger, and then it'll get smaller, 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 the more we go. The reason for this is that the bottom function, so x cubed minus 8, gets bigger much, much faster than x does. So just for instance, let's say that we plug in f of, let's say 4. So then we would have 4 over 4 cubed minus 8. So that would come out to 4 over 64 minus 8. Now, that would come out to a final fraction of 4 over 56. So as you can see, the bottom is going much, much faster than the top is, and the bottom is getting much, much bigger. So when this happens, when the top power of x is smaller than the bottom power of x, essentially the bottom outpaces it. And whenever we're talking about a fraction, that means that we're moving towards, a relatively small number over a relatively big number. And the bigger the number gets on bottom, the closer we're going to get to a value of 0. And the reason I say 0 is, so let's say we have 1/2, and then we have 1/4. Okay, so this is 0.5, that's 2.5. So 1/2 is bigger. And if I keep going, so now I got 1/8, so this is 0.125, and I can keep doing this forever. So 10, 100,000, 10,000, but it'll always be a positive number. It's just that positive number is going to get smaller. So the small that it gets, the number that it's getting closer to is getting closer to 0 all the time. So 0 is the number that we're never actually going to reach, because if you put 1 over a positive number, even if it's a really, really big one, I can put as many zeros here as I want. It'll never actually be 0, the value of this fraction, but it'll be really close to 0. So like this guy is the same as point, and then a lot of zeros. And then at the end I put a 1. So it's not 0, but it's really, really close to 0. And that's why whenever, the powers are like this, we have a horizontal asymptote of y cannot be 0. So to get all of this extra noise and fluff out of the way, now that we've kind of explained, why it works the way it does, the rule is, so if the top power is smaller than the bottom power, well, that means we have a horizontal asymptote, y cannot be 0. So if we were to do the range of this function, the range would be -infinity, comma 0, union 0 to infinity. So all of the numbers except for 0, 0 is the one number that we're not allowed to have. And this is case 1. So in case 1, the top power is smaller than the bottom power. If the bottom power is bigger, then this will be our range every single time, because we'll have this asymptote, this number that y is never going to be able to reach. So that's case 1. So case 2 is actually, it looks a little bit more complicated at first, but it's actually a little easier once you get used to it. We'll do this next one in blue. So let's say g of x is equal to, let's say we have 3x squared plus 5x minus 2. And on bottom, we'll have 5x squared plus 3x minus 1. So, as you may have already noted, they have the same highest power of x. It's x squared on top and bottom. So the highest power of x is that. So here's the logic behind figuring out how this one works. So in this case, we're going to plug in a really, really big number. So let's say we plug in 1,000,000, right? So 1,000,000's really, really big. So if I take 1,000,000 and square it, that is a 1 with 12 zeros behind it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so this number it's almost ridiculously big. So it's so big that it makes that number look small by comparison. And we can keep going up. We can use whatever number we want. So the x squared is going to quickly outpace the x term. Once we get high enough, it doesn't really matter that we're adding 5x. It's there, but it's so small relative to the original, to what x squared is going to be, that we might as well ignore it. Imagine if we added another 13 zeros to the end of this, and then all of a sudden x squared is like, oh, well now x squared has 26 zeros, and it's like, oh, well I guess the x squared is just it's just ridiculously big. And so the same is true for the bottom. So once we kind of, in the largest numbers, we kind of stop caring about both of those. And now that it's just really the x squares we're looking at, if we were to pretend that they cancel a bit, that would leave us with 3 over 5. And believe it or not, that is actually how we find our horizontal asymptote. So that means the y value we're not allowed to have for this guy is going to be 3 over 5. So if the highest powers of x are the same, you just use the numbers in front to make the fraction for your horizontal asymptote. So if we were to do the range on this guy, we'd be able to go for -infinity all the way up to 3/5. And everything bigger than 3/5, so 3/5 to positive infinity, would also be fair game. This is how we describe the range. So I'm going to put up another example, and then we're just going to talk about, how we would go about finding the range for it. Because when it comes to rational functions, the range is actually not the worst thing in the world. So say we have h of x. So h of x is equal to, let's say, x a third minus 5x squared minus 10x to the 7th. And then on bottom, we shall have x to the 4th plus 10x to the 5th minus 2x plus x to the 7th. Okay. Now, there are some things that we can do to simplify this. I'll go ahead and add a plus 2 on top. Okay, so now there's not anything we can do to simplify this. So now, we just want to look at the range. So we just want the range. So, of course, the first thing we want to ask ourselves, okay, what's the highest power on the top? And, of course, the highest power on the top is 7. Highest power on the bottom is also 7. So, okay. So this is going to be one of those cases where we just do or coefficient over coefficient. So we got negative 10 on top. And we don't see anything here, so if you don't see anything, you assume there's a 1. So negative 10 divided by 1, so y cannot be negative 10 divided by 1. So y cannot be negative 10. Okay, so our range would then be negative infinity all the way up to negative 10, and we're using parentheses because we're not allowed to have negative 10. And we'll do a union, negative 10 all the way to positive infinity. So those are the y values we're allowed to have, everything except for negative 10. And that's how you find the range of a rational function. It's much easier than some of the domains we have to find on some of these guys. So, but yeah, and that'll be the range of that rational function. So now we're going to go ahead, go back to the presentation. I believe that's it. So this will be the example that we go over in the synchronous hours, and afterwards we're going to talk about function composition, which is it's an interesting idea. It works a lot with substitution, which is something we've already kind of looked at a little bit. We're going to look at how we formally use it with algebra, but anyway, that'll be in the next video. In the meantime, I hope you have a wonderful day, and I will see you next time. Bye-bye.